Hi, in this video, I'm going to go over free body diagram 1. That's what this is called. We get rid of that, free body diagram 1. So here we go. The first one, as we start doing this, we want to think about, right, there's obviously gravity on things, but then there's also what the other part of this is what is touching it. So, right, as we think about number 1, it has the force of gravity, called weight. But it also has the normal force, right? It's touching the ground, and so the ground would apply the normal force. So it would look like that. For the second one, it slides without friction, right? So if there's no friction there, then we have the force of gravity still, the weight force. We would also have the normal force upwards. And that's it, right? If there's no friction to slow this thing down, you don't need a force to the right to keep it going, right? Since there's nothing slowing it down, you don't need a force in the other direction keeping it going. So let's take a look at this next one. The next one is obviously still has gravity and therefore still has the normal force. Make sure you're making those look equal, so because they should be. And then we have some friction to the left. And so that would be your force of friction, or that would be your force diagram. In this case, we have a force to the left, no force to the right, so that means we would have an acceleration to the left. In this case, it would be slowing down. So next one, we're on this kind of rampy thing. So you got your weight force downwards, and you have the normal force. Now remember, the normal force is perpendicular, meaning it's got to make a 90-degree corner angle. So that means it's got to kind of go in that direction. Let's see here. Then next, this one is going to be pretty much the same idea, except that, so we got weight force, we got our normal force, just like last time. But this time there's some friction that's keeping it from moving. Let's keep in mind that friction has to be parallel to the surface, so it's got to be kind of in that direction. So it might look something like that. Next one, we have the weight force downwards, and we have the tension force upwards. Tension is always in the direction of the cable. So we would have, in this case, tension force, weight force. In this one, we would have the tension force, and the weight force. So those ones are pretty straightforward. Next, we have, right, so this is a perfect example of how you want to think about this in terms of what things are touching it. So, okay, we obviously have our weight force. This object is being touched by the string, so that's going to be a tension force. It's also touching the ground or that surface, so that's going to be a normal force. So the normal force is going to apply a force perpendicular to it, and the tension force is going to apply a force in the direction of the rope. So that's going to look like that. And if you look up, right, this number 5 and number 9 are almost the same, except that instead of friction keeping this object moving, the rope is keeping it from moving, right? So very similar in that case. Number 10, same idea, right? We obviously have the weight force, force of gravity. Then we have two surfaces, right? It's touching this surface and that surface. So each surface is going to apply a force, a normal force perpendicular to it. And let me just label these surface 1 and 2. So that would be N1 and N2. It's not necessary to have the 1s and 2s. That's just to show you that each, like which of those surfaces is applying which of those normal forces. So you don't need to have N1 and N2. It's just there to show you. which one's which. The object is being pulled parallel to the frictionless surface, so that means we have force F in that direction. We would, of course, have the weight force still and normal force. And then that's it, right? It says frictionless surface, so that's all that we would put. Because there is a force to the right and no force to the left, this object would accelerate. Okay, now this one is very interesting. So we have the weight force, we have the force that is being pulled in this direction, and this next one is very interesting because the normal force is actually going to be smaller than your weight force. And here is why, right? This for the force F right here, right? That force is actually supporting some of the weight, right? It has like this kind of vertical component to it where the because we're pulling up on that, we're actually supporting some of the weight of this object. And so, therefore, the normal force, the table doesn't have to support the whole thing, right? If you think about it, if this was like a, maybe a 10-pound object, then the table doesn't actually have to support all 10 pounds, right? No, the normal force is the force that the table has to push up. It doesn't have to support all 10 pounds because, right, someone is supporting some of that force right there. So, um, so there you go for that one. Next one. So this one is complicated because it's got this whole little like pulley here, but keep in mind that we're really only drawing the force diagram for the object. So all of that doesn't matter. We have the weight force down. We got a string attached to the top of it. So that's tension force there. These two are equal lengths because it's being moved at a constant speed, right? It doesn't really matter if it's being moved at a right, that it's going upwards. As long as it's going at a constant speed, you have to have balanced forces. So those two need to be the same length. It looks like T is actually a little bit shorter, but it should be the same length. Okay, this number 14 is very similar to number 12, except our reasoning is a little bit backwards. So we got F here. Keep in mind that the arrows always point out of the dot, never into the dot. So we'd still draw it kind of down and to the left, like so. And then when we think about doing the normal force actually has to be extra big because it has to cancel out the weight force and it has to cancel out the normal or this downward force, right? So it's like pushing down on the object. And so because you're pushing down, the floor has to support both the weight of that block. Let's again think about it as a 10-pound block. It has to support that 10 pounds plus however much pressure and force you're applying down on it. So the normal force is going to be bigger than the weight force in that case. And that's one of those things that is very common to look for on a force diagram. Like lots of people lose points on force diagrams for forgetting to do something like that. Object is falling with no air resistance. So that's the weight force, right? There's actually nothing touching it, so only the weight force. In this case, we would have the weight force, and now it's going at a constant speed, so there has to be some air resistance. So just call it F air. And then number 17 and 18 are trying to trick you because it's traveling sideways. But of course, remember, there's right forces can only be applied by things that are touching it or the force of gravity. In this case, the force of gravity is the only thing that can apply a force because nothing else is touching it. So it doesn't matter if it's at the top or middle of its trajectory, right? It is only the weight force because there's nothing touching it, right? So that's it. All right. Thank you for watching. Hope this helped you figure out the force diagrams.